Hello everyone, my name is Mr. Watkins and I'm the Head of Maths, Computing and Business at Nova Herod Academy. Today our masterclass is on a brief history of maths and computing. This is a really important topic because at this point in our society we're moving to more and more things being made digital, being automated, being based around artificial intelligence, and we need to make sure that our learners are equipped to be able to not only use these applications but to be able to make them and improve them. This lecture is based off one from a Bath Spa University lecturer called Chris Budd, who presented the maths of future computing. In this lecture, we'll focus specifically on how maths has developed and how computers have developed side by side. Because it might seem strange to some people why we have the maths and computing faculty together, but essentially they are so intrinsically linked, they're so connected to each other that we wouldn't have any of the amazing developments we have in maths or computing without the other. So let's get started. So I want to begin with this quote from a CEO of Boeing. They said, "Taking full advantage of computing tools requires more mathematical sophistication, not less." Now I think this is a really important quote because actually when we were learning maths at school when I was there, one of the things our teachers used to tell us is that you won't always have a calculator in your pocket. You need to learn these methods because at some point you might be without a calculator. Nowadays though, we do have calculators in our pockets. We have our phones with us at every occasion or a tablet, and we can use those for a lot of simple calculations we could otherwise do in our head. But this quote draws attention to the fact that actually using a computer or using a calculator does not really require the same level of mathematics as actually making those computers or being able to build further models using them. So we want to make sure that people develop their abilities in maths so that they can then use the technological developments we have elsewhere. On your screen now, you can see the first ever digital computer, our hands. Our number system is based around the number 10. Think about we've got our ones column, our tens column, our hundreds, and where we have a number such as 352, that is 3 hundreds, 5 tens and 2 ones. The reason why 10 is so important to us is because of our 10 fingers. As a developing society, humans needed a way to be able to keep track of their counting, and the hands provided a really nice, simple way of doing this. And actually, in some civilizations, they used a different method. They looked at the knuckles and joints between the fingers, and they were able to count higher on a single hand. But typically, 10, based on the 10 main digits, makes a really nice way of our human system and human mind being able to understand and count. So actually that's the first computer. We use these tools to keep track. They have memory. We can hold up 4 fingers and then we can keep that there until we need to refer back to it. And that's one of the key principles of any computer. So that's the first ever digital computer. Here are some other early computers. And although they might not seem as advanced or as technologically developed as our modern computers, laptops, phones, tablets are nowadays, they are still tools that are being used to compute, to calculate. The first of which is a tally stick. Here you can see this is a very rudimentary way of keeping track of large amounts of numbers. So if you were a harbour master running a warehouse industry for naval shipping, you're going to need to keep track of all the different things coming in and out. And at one point it would have been a tool very similar to this that was used. The second picture is an abacus. That could be something you're familiar with. They are something which were used in schools up until fairly recently, about 50 years ago. It might be more for any grandparents watching this, but it may be used an abacus more at your environment. The picture there is showing the World Abacus Finals. There's an actual international competition around abacus use. This was being held in Japan, where actually abacus use is still promoted heavily to this day. One thing you might notice, if you could zoom in on the picture, is that there are no actual abacuses out on the table. Because actually they've developed themselves to be so good at using an abacus, they can do it through muscle memory. So the talented people sat there doing the calculations, often 8-digit calculations. So for example, an 8-digit number multiplied by another 8-digit number, which would take a long time through verbal methods or through written methods. They're doing that through the use of an abacus or the idea of an abacus. They're counting on their fingers to be able to get to the answer. So that's 2 early computers, early ways of us carrying out calculations and storing the results where appropriate. I want to talk a little bit about a Scottish mathematician called Napier. because essentially he was able to bring in a branch of mathematics called logarithms, and he was able to think of a way of using those to be able to compute more difficult responses. Every computer, even the modern day ones we have at the moment, can only understand really, really basic binary calculations. They can only add or subtract or compare numbers. Anything else they do is down to the ingenuity of people who have developed programs or systems for the computers to use to do more advanced things. So one way in which this was devised was by this mathematician Napier. You can see from the year this was 1614, so this was pre-computers as we know them, and it was more kind of counting machines rather than actual computers. So what Napier was thinking when he was trying to bring logarithms into computing, or to be able to help us do larger computational problems, he was using this fact that any number, here denoted as x, can be expressed as 10 to the power of some value, here shown as a. In a simple case, consider the number 100. 100 can be expressed as 10 to the power of 2. So here a, which is 2, is the logarithm of x to base 10. So the logarithm of 100 would be 2 in this case. The same logic applies for any nice neat power of 10, such as 10 cubed, but this can still be applied to any number. It might be you have 10 to the 0.3214. It can be any value here, and that can then give us whatever value of x we need it to be. Now that we've established that, we can apply this with the laws of exponents or laws of powers or laws of indices. They're all the same thing. Index laws or indice laws come up at GCSE level, but they're things that actually we start covering as early as year 7 in some aspects, and you'll continue to use them through your A-level and degree courses if the students hopefully carry on with that. Down here we have two results being shown. The product of two numbers, product here meaning multiplied together, can be expressed as 10 to the power of something times 10 to the power of something else. Now that makes sense because earlier we established how you can express any value, which we called x originally, as 10 to the power of something. So it makes sense we could call another value 10 to the power of b, and that would give us a different number. Now the law of exponents tells us that if we multiply two numbers that have the same base, so they both have 10 as their base, then all we have to do is add the powers together. For division, a similar result occurs. If you're dividing two values, and both of those values can be expressed as 10 to the power of something, then you just take away the powers. Now, the purpose of that is that suddenly multiplication and division, which are higher order, more difficult calculations than just addition or subtraction, can now be computed as just basic arithmetic. You can see here what started as a multiplicative problem has been reduced to an additive problem. So multiplication and division become addition and subtraction of logarithms. Now this is a table, this is a site which might be familiar to some of the people watching this video. It's certainly not something we use nowadays in our schools. This is a logarithm table. What this is essentially if every number can be expressed in the way I showed earlier, where x can be expressed as any number 10 to the power of a, well then we're going to need to know all those different values of a for just about every number. And that's exactly what's being shown here. A logarithm table tells you what value of a you need to use to be able to reduce it to the number you're after. What that then means is if we were trying to do 13.45 multiplied by 23.56, quite a difficult, complicated multiplication problem, what we can do, we can find the log of 13.5. We can find the logarithm, the letter, the thing that would be a if we had x as 13.45. We can find that to be 1.1287 using these tables. We can also find the log of 23.56 to be 1.3722. Now the beauty of this is suddenly what was really difficult, that's a calculation that would take a long time to complete. If you've got the logarithm tables and you can quickly get the log of 13.5, so that a value, 10 to the power of 1.1287, would give you 13.45. And if you can do the same on this side, Well then in this case, it becomes an additive problem. All you have to do to work this out is to add these two numbers together, and that gives you 2.5009. What we then use is the inverse operation for finding the logarithm, the antilog. So we would do an anti-logarithm for 2.5009. Essentially, we'd look up in the table what value comes out 2.5009. Essentially, it's saying what would 10 to the power of 2.5009 actually be? That's what's being asked here. And the answer is 316.9 based on this logarithm method. If you were to calculate the exact answer to 13.45 times 23.56, which I won't do at the moment, but your students coming through NOVA will be more than fluent in a calculation of that level, it would give you 316.882, which is really, really close to the result we got through using logarithms. So for pretty much all purposes, that's as accurate as we would need to be. So that shows how logarithms can be used to reduce multiplication problems to addition problems. And computers, all computers do is basic addition and basic subtraction. So now they can do multiplication and division. Let's look at a couple of really old but really amazing computers. The first shown here is called the Antikythera or Antikythera, which is a Greek computer. It was discovered under the sea and it's been estimated to be over 2,000 years old. So this is a computing device that is well over 2,000 years old, and it was used to calculate the movements of planets and stars and to work out when the next eclipse would be, which is a really, really incredible thought to think that 2,000 years ago the ancient Greeks were so mathematically advanced that they were able to predict interstellar movements just using tools such as these, essentially a cogwheel set to be similar to the universal setup. Another impressive machine here is one of Pascal, who's a famous mathematician's machine. This is called an adding machine, and it's a bit of a simpler one. It's also a fair bit more modern. This is hundreds of years old as opposed to thousands, which literally by turning the wheels on there, it would add numbers together, which now that we have a calculator, I could punch in 582 times or add 3,631 and get the answer in a split second. Before we had that, a machine like this would be incredible because all of the financial industries and anything to do with economics would really be relying on people being able to add up things quickly. And I mentioned earlier, as in any traders, any harbour masters, any people, quartermasters who are keeping track of things, a machine like that would be really, really useful. I want to talk now about a famous mathematician called Charles Babbage, who was alive in the 19th century. Babbage wanted to calculate the results of complicated formulae. And actually, it wasn't just Babbage by himself. As a civilization, we needed to be able to work out when certain things would occur, or how long it would take to travel certain distances, or well, it's all based around astronomy and navigation, essentially. There were different formulas that were being derived. A lot of these formulas involved the sine, cosine, and tangents, so they used trigonometric formulas that we learn more about in our year 10 and 11 GCSEs. But actually, pretty much any formula that uses trigonometric ratios can be reduced to what is called a polynomial function or a polynomial formula. Here you can see a polynomial formula example being shown. This tells us that we can find a value called y by carrying out 1 plus 3 over 2 lots of x squared plus 1 over 2 lots of x cubed. That would be the approximation for a formula that might be needed for some form of astronomy or cosmology or some navigational problem. Trying to measure things like the tidal differences and the speeds you might need is a really complicated thing. So they would try and use formulas like this. Now, what they did is they thought computers can't solve this. Computers can't solve trigonometry, at least they couldn't at this point. They can't even do this. So Babbage thought, well, computers can basically only add and subtract. So I need to get a way where I can reduce this polynomial to just an additive or subtractive problem. What we can do is substitute in different values. If I was to put 0 into this equation here, I would have 1 plus 3 over 2 lots of 0 squared plus 1 over 2 lots of 0 cubed. Now where we've got a 0 being times by 0 and a 0 being times by 0 and 0 again, that essentially reduces this to 0 and this to 0. So if I was to substitute in x is 0 into the polynomial shown, it gives me this value of 1. If I was to substitute in x is 1, so I'd have 1 plus 3 over 2 lots of 1 squared added on to 1 over 2 lots of 1 cubed. It would give me the result 3 when x is 1. We can then do x is 2, x is 3, x is 4, and it can continue in this fashion. Essentially what Babbage noticed here is we can substitute in and we can find x values. I could then find the difference between the numbers being found. So you'll see here, between 1 and 3 is a difference of 2. Between 3 and 11 is a difference of 8. Between 11 and 28 is a difference of 17. And between 28 and 57 is a difference of 29. Now this isn't a mystery why this turned out. This is what's known as a cubic formula because the highest power of x is 3, so it's a cubic. If the highest power was 2, it would be a quadratic. We can find the second order difference by finding the differences between the differences, and you can see why this is called the difference engine. There's lots of differences going on. This row here was the differences between the substituted in values, or the solution to the substituted in values. This row here is the differences between those differences. So between 2 and 8 is 6, between 8 and 17 is 9, between 17 and 29 is 12. Doing that one more time and finding the third order difference, between 6 and 9 has a difference of 3. Between 9 and 12 has a difference of 3. And this pattern would continue. What this means is we've reduced the trigonometric function to a polynomial, which then through substitution and getting some numerical values in there, we can see if we take the third order difference, there will always just be a 3 difference between them. So to find the next term, all I would have to do is add 3 onto the second order difference, which then means I'd have to add on 15 here. So that would give me 44. And then that means all I have to do to find the next term is to do 57 and 44. And suddenly, the trigonometric reduced to polynomial reduced to numerical is being calculated through just simple addition. So here in this case it'd be 101. That would be the next term. So we could find any term we want during this. I could find the next one by adding 3 more on. Get 18 and then keep going in that fashion. I won't carry on because we won't have all day for that. But it showed how we can reduce any mathematical formula essentially to this type. And from that we could calculate lots of different things. If it was a higher order polynomial, if it was a quartic or a quintic, so if it had powers of 4 or 5, it would just mean we'd have to go down a bit further in our difference table to find the common difference. This is really similar to a topic called linear sequences that students do around Key Stage 3 and also comes up at GCSE, and then it goes further into quadratic sequences and even geometric sequences later in GCSE. So Babbage made his machine, and his machine would work for any polynomial. So he was working on a machine that could calculate the values at any point for some really complicated formulas that were really useful for a range of applications, and as I mentioned, predominantly navigation, astronomy, and actually a lot of financial calculations too. It's mechanical. Being able to find the next value is just going through the motions of adding 3 at the right point, finding the next difference, finding the next one. So Charles Babbage basically thought, well, if that's the process I can do, then I can mechanize it. And he developed a difference engine, or the idea of a difference engine. He never actually got around to finishing it. He was granted £17,000 by the government to make this, which in today's money is around £1 million. So a lot of money being given to him there to work on it because the validity of it and the purpose was well regarded. People knew it was going to be something that was going to be really useful. So he then started his work on it. And he was thinking, what does it need to do? Well, firstly, this is the principles of modern computers as well. And this is what Charles Babbage was thinking in his computer. Firstly, it had to be able to represent numbers to a certain precision. The more decimal digits we use, the more accurate the calculation. But then it's harder to store them, and the slower the resulting calculation. So secondly, it must be able to store these numbers for at least a semi-permanent amount of time. So to calculate an nth degree polynomial, it must be able to store at least n plus 1 numbers. So if we're doing a third degree polynomial, it must need to store 4. And thirdly, it must be able to add these numbers quickly and accurately. Here's a shot of the idea of how the difference engine would work. Here, numbers are stored as columns. A column of cogwheels. The cogs would be set so that each position represents a decimal digit and each column a certain number. The longer the column, the more accurate. So you can see here there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this could do 14 digit numbers in their calculation. And then the numbers are added by literally turning the cogs. As one cog turns, the other cogs turn. In his prototype, Babbage designed an idea with 3 columns of 6 cogwheels. In the Science Museum at the moment, there is an example of the machine with 8 columns with 31 wheels visible. So being able to do some really advanced calculations there. This leads us into the next person I want to talk about, Ada Lovelace. Ada Lovelace and her mother, Lady Byron, went to see the prototype that Charles Babbage was working on in 1833. And this is what was said. We both went to see the thinking machine, for so it seems, last Monday. It raised several numbers to the second and third powers and extracted the root of a quadratic equation. It might not be clear from the tone, but they were very, very impressed with this. Essentially, they are amazed that a machine can think, or at least appear to think. And it was able to solve a quadratic equation through a mechanical purpose. That's something which we can now do fairly fluently, but for a machine to be able to do it at that time was incredible. Now, unfortunately, Charles Babbage was an amazing inventor, an amazing mathematical mind, but he was easily distracted. So he actually abandoned his project in 1842 to work on a more advanced version of a computer. This is Charles Babbage's and Ada Lovelace's analytical engine. This is a more advanced computer. This used punch cards for memory, so it would keep track long term of the calculations it could do. The problem with this machine, though, it was an amazing prototype, but when it came to the actual use, because there was so much actual mechanics going on, so many cogs moving, so many pistons, well, not pistons, but so many things going on, it was not able to actually operate long term. So it was a fantastic idea, and it helped lay the groundwork for all future computers, but in practicality, it never really took off. It was too expensive to be useful, but an amazing machine, an amazing way that computers can calculate. Ada Lovelace was interested in particular with a type of numbers called Bernoulli numbers, which are represented in the mathematical notation here. I won't go through the complexities of it, but essentially it's a special type of number which crop up in lots of different purposes. So she wanted to come up with a way of getting Charles Babbage's theoretical machine, that analytical machine we just saw, to be able to calculate and find other values using it. Now, Ada Lovelace is credited as the world's first computer scientist. And here you see the first ever computer program. So think of all the amazing computer programs and apps we use nowadays. This is literally the first program. This is her telling the machine, or writing the instructions for what she's going to tell the machine to do. The human race is incredible. Computers are very, very, very basic. They just add up, they just subtract, they just compare. But we're able to write such advanced, we're able to think in such a way that we can get the computers to be able to understand what we want. We give them really, really specific commands using programming languages that have been, again, developed by humans to be able to get them to do whatever it is we need. And here, this computer program will tell it to calculate Bernoulli numbers based on the given inputs. So an incredible piece of history there, the first ever computer program. This brings me to the end of my session today, where I was hoping just to talk a little bit about some of the amazing early developments of the human race in computing and mathematics, and just to really build up that link. Computer science is one of the main branches of mathematics. Mathematics being a huge, amazingly interesting subject, which can go in wildly different directions. You might be interested in cracking codes and ciphers, you might be more interested in modelling the universe, it might be that you'll use it in more of a scientific statistical analysis measure. Or maybe you want to use maths so that you can understand computers and make them do exactly what you want. So just to summarise, humans have always been computers. We're always looking at ways of improving our ability to calculate. And really importantly, maths is intrinsically linked to computer science. Everything computer science everything computer science owes itself to very advanced and very simple maths. Thank you very much for listening. This has been Mr. Watkins going through a brief history of the early computational devices in maths. Thank you very much.